Back in 2021, I made a clock out of Legos. It was bodged together over the course of several months, and I just barely got it working. It was bulky, loud, lacked features, and frankly, I didn't like how it looked, even being someone that doesn't usually worry about aesthetics. So after I took it down, I decided I would make another clock that would fix all the problems of the old one. As my Lego building skills have improved since then, I also decided I would build it entirely out of LEGO Technic, and not use regular bricks unless I absolutely had to. It has taken me over 3 years to get it to the point at which I would say it's complete. Undoubtedly, I'm going to continue to tinker with it, but if I stopped now, I would be more than satisfied, and so I'm documenting my efforts thus far. This is my second clock. I do admit to kind of cheating with this because it's not a purely mechanical clock. It uses an electric motor and a microcontroller to keep time, as you can probably hear. But all of my other goals have been achieved, including making it look better. It has all the features of the old clock and more. In addition to the concentric hands and day of the week indicator, I was able to add a rather power-hungry mechanism, an hour strike. The power for this clock is provided entirely by this electric motor. It's one of the old 71427 9-volt motors, because they run extremely quiet compared to the modern power functions motors. This photo interrupter in there, it's hard to see, and a little black wheel that's spinning through it, send a signal to the microcontroller every sixth of the rotation, and it compares that signal to the mains frequency and sends pulses of power to the motor to keep it running at exactly 300 RPM. The rest of the timekeeping is just a whole lot of gears that progressively reduce the rotation speed of the motor and produce outputs that rotate once every minute, once every hour, once every 12 hours, and once every 24 hours, and once every week. Before I move on, I'd like to point out this knob in the front. This is how the clock is set. When I pull it out, it disengages the gears and allows me to push the hands around. The back half of this clock, the striking mechanism, has a lot of levers in addition to a few gears. It's based off a striking mechanism in a video by Kevernista, mostly, but not exactly. Every hour, the red beam on the minute hand shaft comes and releases this ratchet, which allows the hour marker arm to spin until it hits this cheese slope. And the position of the cheese slope is synchronized with the hour hand. They're geared together. When the hour counter arm moves out of its zero position, this set of levers fall, and this toe ball link here engages a driving ring. But nothing actually turns because this quarter circle arm on the minute hand shaft has also disengaged its own driving ring. At the top of the hour, this whole, both of these levers fall, simultaneously re-engaging this ratchet and this driving ring. And now power can turn the striking shaft. As you just saw there, on every turn of this hour striking shaft, this toe ball ratchets the hour counter arm back by 1 hour's worth. And this white piece rings the bell. When the hour counter arm ratchets back to the zero position, it lifts these levers up and disengages that driving ring. However, the striking shaft continues to turn because there's a second driving ring here. This is only disengaged when the hour counter striking shaft is in its home position, which is where it is now. If I turn it past that and allow that driving ring to re-engage, it does another turn. That is controlled by this red cam in the back. Oh no, I broke it. Well, there it reset itself. But in essence, the three striking rings implement a Boolean logic function. I've recreated the gears here so you can see what's going on. For the majority of the hour, only the first driving ring is engaged, and no power can be transmitted from the motor to the striking mechanism. 15 minutes before the hour, that quarter circle cam disengages this driving ring, and now they're doubly disconnected. When the counter arm ratchet is released and the arm moves out of the 0 position, it engages the middle driving ring, but they're still disconnected. And here's the important part. At the top of the hour, this one engages again, and now they're connected, and the motor can drive the striking mechanism. And then as the striking shaft rotates and the red cam in the back moves out of its home position, it also engages that driving ring. What happens with this one is that once the hour counter arm moves back to its home position, the 0 position, it disengages that, but they're still linked. So it continues to turn until this one disengages, and then we're back into the normal state. The effect is that whether the chime train is connected to the motor or not is a Boolean function of these 3 inputs. If you count engaged as true and disengaged as false, then the top 2 driving rings form an OR gate, which is then ANDed with the third one for the final output. The one important part of this striking mechanism is this little cheese slope that stops the hour marker arm is pivoted, so it can slide under the hour marker arm when the chime changes from 12 o'clock to 1 o'clock. Big thanks to Cavernista for figuring out this construction, so I didn't have to waste time figuring it out myself. I can't stress how important this is for the peg to be pivoted, because if it isn't, the clock will literally jam every 12 hours. I also added a strike disable lever here. All it does is catch the hour marker arm so it can't move out of the home position, and nothing happens when the top of the hour is reached. And now I get to talk about the electronics. Being someone who's studying electrical engineering in college and not mechanical engineering, I'm actually a bit embarrassed there's not more electronics here. But then if it were, it wouldn't be a mechanical clock. The circuit may look complicated, but it's actually very simple, even on the software on the microcontroller. It just looks complicated because I've used really long jumper wires. And again, like many of the circuits that I have shown or will show on this channel, it's based around the amazing little ATtiny85 microcontroller. The input transformer here outputs 6 volts AC. This is then rectified by 4 diodes and filtered by a couple capacitors and a 7805 down to 5 volts powering the microcontroller. This is a very old breadboard. It's kind of finicky. Don't touch it, or it's not going to work. Power also goes through this gray wire to the photointerrupter, which I mentioned in the beginning. It sends pulses back to the microcontroller. The motor itself is the fastest rotating shaft at 300 RPM. The counter wheel rotates at 100 RPM, or 5/3 of a turn every second, and combined with the 6 holes in the disc, the microcontroller receives 10 pulses every second. The way the microcontroller regulates the motor speed is this very bad implementation of an integral controller. Every pulse from the sensor reduces the error variable by 6. The raw AC signal from the transformer is filtered by a resistor-capacitor low-pass filter, and each pulse increases the error variable by 1. And then the microcontroller just checks the sign of the error variable. If it's negative, it increases the duty cycle of the PWM signal sent to the motor, and if it's positive, it reduces the duty cycle. This then goes out one of the pins to this small transistor here, which then feeds the motor. I've programmed it to count out 6 mains pulses for every wheel pulse, because the mains is 60 Hertz where I live. You can probably guess what part of the world. If you're building this for yourself and you live in a 50 Hertz part of the world, there's a marked line in the code, change it to a 5. The link for the code is in the description of this video. Unfortunately, I made the control loop run way too fast, and so the duty cycle spends most of the time at either 100% or 0%, and the motor ends up getting these irregular pulses of power and makes this ticking noise, which I really didn't want with the motor running continuously, but I fooled around with this for 6 hours and couldn't get the ticking noise to go away. So it is what it is. I'm not going to fool around with it for any longer, because despite that ticking noise, there's actually a bigger problem. The clock loses time. In theory, it shouldn't, because the mains frequency is carefully regulated by the power company to be exactly 60 hertz, because, well, there are electric clocks that use synchronous motors that rely on that frequency to keep time. But this one, even though it's programmed to keep perfect time, doesn't. And I don't know why. My best guess as to why is that a lot of the computer equipment in my home that uses switch mode power supplies doesn't have the proper filtering on the input side. And so some of that noise makes its way back through the power lines, through the transformer, and shows up as random noise in the AC output, which the microcontroller then interprets as extra pulses. Although if that were the case, it should be gaining time and not losing it. So I really don't know what's going on. At any rate, I'm not actually using this clock to keep time during the day, so I'm not that concerned. Well, I hoped you liked this clock that I made. If you did, press the like button. And if you're interested in seeing more mechanical and electronics projects in the future, you can subscribe to my channel so you don't miss them. I'm probably not going to upload again until the new year, so happy holidays.